try Canvas first, and I know that some of you already submitted. The second announcement is, three announcements actually. So second announcement is about the homework. There's a homework due next week, I think. And at least technically we've covered everything that you need to do the homework. That doesn't necessarily mean that you can do the homework. I mean, you probably have to try, and it's not the easiest homework to do. So please spend some time. I'm not saying that it should be necessarily difficult, but in the past these questions have been more painful than the other stuff. Yes?
The second part, the counting, I mean basically count the number of possible decision lists.
Yes. Yes.
Is that, I mean, you gave us a hint that that analysis can be done on that paper, and I'm just wondering, like, is it complicated enough that it can take a long time to figure out that?
Not really, no.
Oh, okay.
It's not. I just wanted to mention that the answer is in the paper.
Okay, because I didn't want to just give up and look at the paper.
Yeah, don't do that. I mean, in general, I would say try it before you give up. But
Depending on the difficulty level, if you're afraid.
give it a shot first.
Okay.
It's not the hardest. Let me put it this way. At some point, I considered putting it on an exam sheet.
Okay.
Then decided that I ran out of space. So, other questions about homework?
So it's due on Tuesday, right?
It's due on Tuesday.
Okay. What about Thursday?
What about Thursday? It's another day. Yes.
Thursday.
It's a good day. Yes. Probably by then you'll be doing homework 4. So we are on a tight schedule with respect to homeworks because we are coming close to the end of the semester and we have 2 more to do. And some of you I know were kind of annoyed with the first 2 homeworks because there was just so much programming. And I figured, let's have a homework where there's no programming. But then the next homework will be back to the old mix of programming and theory. But just to another announcement is, unfortunately, I won't be having office hours today. But the TAs will have office hours. There's one tomorrow, there's one on Monday, and there's one on Tuesday that's mine. And if there's popular demand, we'll try to hold one more office hours somewhere in the middle. Not in the weekend, but one of these 3 days. Any questions?
Can you talk a little bit more about what you're looking for in the assignment that's due today? I know it's well specified.
Sure. So, frankly speaking, I just need to know that you've been doing something. What that means is, tell me what you've done for your project, any pre-processing for your data that you might have done, any literature that you might have read. In particular, tell me also about how you will evaluate success. If you're, for example, if you're building a training a system, this is not for the projects that are theoretical, but if there's most projects are not. If there's a project that talks about, we're going to build a classifier that does X, then you should tell me what you count as success, accuracy, or describe your data set. Fit it all in 2 pages, no more. And the other thing that you can also do is, if, for example, this is a problem that other people have worked on, most likely that's the case, then briefly, maybe in a few lines, describe what other people did and cite a paper if you can. So I just need to know that you've been thinking about your project and you won't start your project the day before it's due at the end of the semester. And so this is a way to force you to do that. Does that seem like 2 pages worth of material?
Yeah.
Okay. Other questions? Okay. Oh, yes. The one other thing is in the homework, question 1. So I'm not going to. It's actually an easy question. Okay. Let me start with that caveat. But there's an answer that is extremely easy and extremely obvious, and we're not looking for that. The true answer, the actual answer we are looking for, is also very easy, But think of the most trivial solution. So let me give you one more hint. You're supposed to come up with a function, a feature expansion function, which takes you from, I think, x1, x2, the two-dimensional space, to some other space. That other space should not be one-dimensional. If it is, then think about it, and we will not be pleased with that answer. Let's put it that way. The problem with what I'm saying right now, I'm being necessarily vague because this is actually a very easy question once you know the answer. And so it's hard for me to actually give you a hint without giving you the answer. But I can tell you this much. Do not give me a function that takes you from the two-dimensional space to a one-dimensional space. Are there any questions, any concerns about the homework or the intermediate report? Okay, so we've been looking at the theory of learning in the last maybe 3 or 4 classes, and now we're going to move on to back to the applications. By applications, I mean algorithms, and now we are going to look at algorithms, but enlightened by the fact that we understand what learning is. So in this lecture, we're going to look at the idea of ensemble classifiers, and in particular, we are going to look at this one algorithm called AdaBoost. So I'll start off by talking about what's boosting. I'll describe the algorithm itself, and then finally end up with this general discussion about ensembles and why they are actually one of the most useful things in your machine learning toolbox, especially if you're trying to implement classifiers on real life problems. So before getting into ensembles, let me introduce it, the idea of ensembling, through this one particular method called boosting. So boosting is a strategy for constructing a strong classifier if you have a collection of weak classifiers. And there are formal definitions of these strong and weak learners, and I'll tell you what they are. And a lot of this goes back to a few papers that came out in the late 80s. So probably older than most of you here. Boosting is actually a very useful algorithm, and it's a strategy for constructing a classifier that has a strong pack guarantee using only what might be thought of as rules of thumb. And it's an ensemble method, and ensemble methods are these general strategies for constructing classifiers using other classifiers. So let's say you want to build a detector for let's say whether a pitcher has a car or not, and you come up with many rules of thumb. Is there a wheel? Yes or no? If there is a wheel, you say car, else not car, and things like that. And now you want to combine these rules of thumb into one big classifier, and that classifier is called an ensemble. In some sense, it's basically just think of it as a committee of deciders, and each of them vote for the final answer, and the final answer is a consensus decision. Boosting is a method for ensembling that has strong theoretical guarantees. So to introduce boosting, I'm going to use an example. So a lot of this material comes from a talk that one of the authors of AdaBoost, Rob Shapir, gave, I don't know, in the 90s. So the examples are definitely dated. So say the goal is to classify a phone call into different types. If the phone call, let's say that we are able to transcribe the text and all that, and the person at the other end says, I would like to place a collect call, and you want to label it as collect. If someone says, I need to make a call but bill it to my office, then you have to label it as third number, and things like that. So there are a bunch of labels. And you can come up with the rules of thumb. The rules of thumb could be something like, if the word card, let's say card occurs, then you make it a calling card. If the word collect shows up, then label it as collect call, and things like that. But while it's so easy to come up with rules of thumb, and these are the kinds of things that you would write, if you don't know about classifiers and features and such things. Tiny little programs, which are probably okay, but are very weak. They'll miss most cases. What we would like to do is combine these rules of thumb into a single prediction. This idea is called boosting. You have these weak predictors and you want to boost their strength into getting a strong predictor. And one strategy, which was actually, which seems reasonable, is get a set of examples, build a rule of thumb. Get another set of examples, build another rule of thumb. And keep doing this till you basically run out of time or patience, which in the technical terms we call it repeat t times. And finally combine these rules. So, well, obviously there are a few things that are missing. One, how do you know which examples to select? And the second one is how do you combine them? And boosting is a way of answering these two questions. So, is the general setup clear? Before we get into formal definitions and math. Yes?
For this one, for the feature space of all the examples, I'm just seeing that this could cause some issues because, for example, you're saying that for the calls we should make if a word appears or something like that, a feature. But what if we...
That's not a feature, that's just a classifier actually. But go on.
But what if we don't know the key feature that should be used to classify it?
Right, so yes, I agree, and which is why any single thing, any single rule that you come up with is not going to be good enough. And the hope is if you have many of them, probably infinite number of them, you want to just combine them into a single decision. You know that any one of them is bad, but you want a consensus decision that is as good as it can be. Yes?
Is this similar to the idea of like a forest of decision stumps?
It's actually very, very similar. In fact, that's probably the last slide of this lecture. The idea of forests, or it's called random forest, is an ensemble, another ensemble algorithm. So, the reason, yes?
So basically what we're doing is given some data, we're mapping the data into a feature space of Boolean features, and then using those features.
That's one way of thinking about it, in fact. Yes. Each of these rules of thumb can be seen as feature generators. But what if they themselves are learned? And you have an algorithm that can learn those things, but not the higher level classifier. So, to formalize this a little, I want to remind you about pack learning. And at least for the context of this lecture, I'm going to call it strong pack learning, which is, this must look familiar. So, you may have any distribution over examples, and for any epsilon and delta, which are small numbers, less than 1, greater than 0, given a reasonable number of examples, a strong pack algorithm will find a classifier whose error is less than epsilon, and it will find it with high probability. It will find it with probability 1 minus delta. We've seen this before. So this is a strong pack classifier because we are saying that epsilon is greater than 0. We are not saying epsilon can be arbitrarily close to 0. Right? We can, if there are enough examples, we can get the classifier to be as good as we want. A weak pack algorithm is exactly the same, except I'm going to read out what it says there and then explain it. Epsilon is greater than half minus delta. Delta is some small number. Basically what that means is, if you have a binary decision and let's say it's both plus and minus are equally likely, if you toss a coin, it's going to be right half the time. What if I have a learning algorithm that gets you a classifier that is right only slightly better than chance, meaning the error is more than half minus delta, just very close to chance, but better. So, is the difference clear? A strong classifier lets the error go down to as close to 0 as possible, as you want. A weak learning algorithm actually is not a strong classifier, a strong learning algorithm And a weak learning algorithm can learn the concept, but is going to be pretty bad, only slightly better than chance. Does the difference make sense? So clearly, in order to define these things, we need to understand pack learning. But once that comes up, we can start thinking about these different algorithms. There was a 1988 paper by Michael Kearns and Leslie Valiant asked the question, does strong learnability imply weak, no actually the other way around, does weak learnability imply strong learnability? What that means is, say I give you a concept class, some concept class, and I tell you that there is this algorithm which is a weak pack algorithm. Does this mean this concept class is pack learnable? If I am able to produce a classifier for any concept that is just slightly better than chance, can you somehow improve that decision? So can you produce a classifier that can be arbitrarily good? Can you come up with an algorithm, or maybe prove that it's possible? Questions?
What are the bounds on gamma? Because could you just say gamma can be anything between
0.5.
Yeah.
Yes.
But then your error could potentially be arbitrarily small.
It could be arbitrarily small, but yeah, you're right.
So is gamma like fixed maybe?
No, gamma is another parameter actually.
Okay.
So this slide might need some reworking, but basically you have a class. The gamma becomes a parameter that eventually shows up in all the theory.
Okay.
If gamma is larger, then we might have to pay more.
Okay.
So, or actually the other way around.
The sample complexity would maybe change.
Not exactly. We'll see what it is in a minute. So obviously the answer to this is yes. Weak learnability implies strong learnability because there's an entire lecture about this. And the whole lecture is about the story of the answer to this paper. Yes?
Can I just ask one more quick question? So I kind of forgot, we had this whole thing with pack learning, but did we ever say something like there exists an algorithm that has...
No.
Okay.
No. Pack learnability simply says any learning algorithm which, for example, in the Occam's razor version, any learning algorithm that's consistent, that produces a consistent classifier, will make small number of errors if you have these many examples. It's always an existence proof rather than if such an algorithm exists, then this algorithm will be good enough. It's still the responsibility of all of us to come up with algorithms for things that are pack learnable. Okay, so this is the game that we are playing. We are trying to see if weak learnability implies strong learnability, and thankfully this game has been played before, and I'm a big fan of history, so let's look at the history of boosting algorithms. This question was asked in 1988, and in 89 Rob Shapir came up with a paper. He proved, and that was a paper that had a little while in the beginning of this talk, he proved used in a constructive fashion by actually producing an algorithm that boosting is possible. And it's a recursive algorithm that repeatedly calls the weak learner on multiple times. A year later, your friend came up with another algorithm that is another boosting algorithm. And then Shapir refined it, and this was the first time there was some practical, no actually there was some experimental results, but it didn't work very well practically. And then all this led into this paper from Freund and Shapir in 95, where they introduced this algorithm called AdaBoost. And AdaBoost was not only, it had very strong theoretical guarantees, but also was actually practically easy to implement and worked. And in fact, I'm still not sure, but it's possible that you guys might implement it in your next homework. There's a lesson here that AdaBoost actually was, it turns out it was used in many, many places. In fact, I've seen it show up in many, many applications in NLP, in computer vision. And it also got a Godel Prize for Freund and Shapir. So there's a lesson here for people who are doing research. You know, you start off with a first cut solution. It may be terrible. It's just a proof of concept, and then you keep refining it. And after maybe 6 or 7 years, you'll get an answer, and maybe after another 10 years, you'll get a Godel Prize. So you know, life is good. Anyway, this is just a history lesson. Let's go back to the algorithm itself. So let's talk about AdaBoost. AdaBoost is actually a constructive proof that answers this question of whether weak learnability implies strong learnability. And to introduce the algorithm, let me use a toy example. Let's say we have a bunch of examples, and our weak learners are in one of these two lines. Either a horizontal line that separates positives and negatives, or a vertical line. Clearly, there is no weak classifier that can separate this data, right? The big change that we are going to have in discussing this AdaBoost is we are going to assign an importance to each example. How important is each example for finding a classifier? And we are going to assign a numerical score. In the beginning, all examples are equally important. So the learning algorithm will treat each of them as important and try to find a classifier. And let's say it finds this. And let's call this classifier H1, this line here. Clearly it's made mistakes. There are 3 mistakes. So there are 10 points, so the error is 0.3. We'll call that epsilon 1. Okay? So now the key point here is what we'll do is we'll keep calling this weak learning algorithm again and again. Each time we will decrease the importance of all the examples that our previous classifier predicted correctly, and we'll increase the importance of all examples where we made mistakes. So those 3 points become important in the next round. So I'm using the size of the plus or the minus to illustrate the importance. So these 3 points where the classifier made a mistake become more important, and the other points become less important. And the whole game is about how this importance is carried along. So I'll use this notation D sub t. It's just a set of weights, one for each example, and it's one way of thinking about it is how important is this example? Say dt of I is how important is example I for the learning algorithm when it finds the next weak classifier. So right now, in the beginning, dt of I was uniform, so it is 1 over m, where m is the number of examples. But now we've upweighted some examples and downweighted them, and with this new set of weights, let's say the learning algorithm finds another classifier. We'll call it H2. Because the 3 big pluses were important, this classifier, is somehow it finds a classifier that correctly predicts them, right? But it clearly makes more mistakes. This time it makes 3 mistakes, right? Let's see. Yeah, it makes 3 mistakes, the 3 minuses here. And I'm going to argue that this has error, if we just calculate the error as, number of mistakes divided by number of examples, it should be 0.3. Right? There are 3 mistakes, 10 examples, it's 0.3, but I'm going to argue that the error is not 0.3, it's less than 0.3. Because these 3 examples are not important. They carry a weight that is not 1 over m, but something less than that. Is that intuition okay? And in fact, I'm going to define the error slightly differently in the interest of first throwing the math on the slide and then working through it. Here's the error. It's a function of the d sub t of each example. So let me show you why this is a reasonable definition. So just let's take 2 simple cases. H is a classifier and Y is a label. So case 1, when h and y disagree. So h is +1 and y is -1, or vice versa. In that case, really, in this case, h of x times y is -1, right? Now let's say there's some, let's assume that we have only one example. If we have only one example, this summation goes away, it's just this one thing. So in this case, epsilon will be half minus times -1. I just plugged in everything into this expression. If now dt was uniform, meaning every example was equally important, this quantity, in this case, suppose we have only one example, this would just be 1, right? We have only one example, and that one example is equally important, which means dt is 1 over 1, which is 1. So this becomes half plus half, which is 1. If every example is equally important, then making a mistake on this example counts as losing 1 point. On the other hand, let's say this example was not that important. The d sub t was some number less than 1. Then you lose less by making a mistake on this point, on this data point. If it was greater than 1, then you lose more. Or actually, it can't be greater than 1. If it's a bigger number, you lose more. And this is the case for when you make a mistake. When you don't make a mistake, y times h is equal to +1, because y and h are both equal. And you can plug it in, you basically don't lose points for making mistakes on those examples. Questions about this definition of error? Yes?
I have a question about how dt is initialized.
Uniform.
Okay.
In the first iteration, every example is important. That was the picture that we had at the beginning, this one.
Okay.
All examples are important, you make mistakes, and then the ones where you make mistakes become more important.
Okay.
Yes.
Is the sum of the importances 1?
Equal to 1.
Oh.
Yes. And this is just for the sake of intuition, and I'll be going into the gory details of AdaBoost very soon. But other questions? Yes.
Am I getting off base by automatically starting to make connections to window here?
Not quite actually. I don't know how you got there though. Why do you think that?
Because if we get something right, well, it's kind of like the reverse of winnow. Whenever we found a variable was important, we upped it. Whenever we're making a mistake,
yeah. But see, the thing is, that's actually an interesting connection, because we will be doing something similar, except in Winnow we were promoting and demoting features. Now we're promoting and demoting examples, right?
Yes.
But that's an interesting connection, because a few years after the AdaBoost algorithm came along, it turned out it's also a multiplicative update in a different context, in a different space. It is a multiplicative update algorithm, but not in the space of weights. Other questions? Yes?
How much importance do you increase after the first round?
After the first round? Hold on to that question. Actually, this upweighting and downweighting is a function of the error that the classifier makes, of the total error. And we'll see exactly the expression. It's a multiplicative update actually, and we'll see exactly what the update is. Okay, actually those are all good questions, and so I'm happy that at least there's some. I'm happy that I'm not totally off base. So, right. So we learned this classifier x2, and it has some error, but it's not. The error is not the distribution over the examples is not uniform. So that's the error is weighted by that distribution, which is dt, and we move along. So what we do now is we again upweight all these examples that we made a mistake over, downweight all the others, get a new distribution over the examples, and at the same time we also remember this new classifier that we learned. So we now have in our bank H1 and H2. We've learned 2 classifiers. We've done 2 rounds of boosting. Now we have a third set of, the same set of examples but another distribution. We learn another classifier, this time it's some horizontal line, and let's say this error is 0.14, we just remember it, and again for the same, it also makes I think 3 mistakes, this time it's 1 minus and 2 pluses. There's a minus on top and 2 pluses at the bottom, and again this mistake is not 3 divided by 10, it is weighted by the error. Remote question.
Is M the number of examples?
Yes, M is the number of examples. So at the end of this process, let's say we stop now because there are only so many pictures I can fit on a slide. So we stop now and we end up with 3 different classifiers, and we don't report any of those 3 classifiers independently. We build a consensus classifier, I call it H final, which is actually just a weighted combination of these 3 decision functions. So think of these weights, alpha 1, alpha 2 and alpha 3 as votes. When a new example comes in, H1, H2 and H3 each make a prediction. But their prediction, and then finally the final classifier, capital H, takes all their predictions and builds a consensus. But to build a consensus, it does not weight each of these classifiers equally. It says H1 has got alpha 1 number of votes, H2 has got alpha 2 number of votes, and it takes the combination of them. And that is the final output of the final classifier. So none of the weak classifiers show up. H final is the strong classifier, it turns out. So just to summarize what I just said in one slide, you're given some training examples. X1, Y1, X1 is a feature set, let's say some instance, and Y is a label. Xi, Yi, you get M such examples. And for nearly all this discussion, I'll assume that positive is +1 and negative is -1. And what you do is you play multiple rounds of the following game. In each round, you construct a distribution dt over the examples. You have m examples, so your distribution is over these m objects. And the way to think about this distribution is how important is the ith example for my next learning algorithm. So the key thing to note is somehow you have to modify your learning algorithm to respect this importance. We've not seen that explicitly in the class, though I know that many of you asked me after class and in office hours how to do that, and most of you who asked me this question came up with an answer by yourself. So I encourage you to think about it. So you have this distribution and you find some classifier H, T, which is a weak classifier, and it has a small mistake, epsilon t. You do this t times, so you have t classifiers and t errors. After t rounds, you combine them all into one final classifier, and you just report that. This is a general outline of boosting. Question?
In an ensemble method, like in this example I saw, we have like multiple splitting planes. So it's like increasing the expressivity.
Oh, that's a wonderful observation.
So
Yes.
I was wondering, is that what accounts for the increased accuracy, is the increased expressivity?
Yes.
Okay.
That's one of the things. So that's only one of the things, because the other thing that also shows up is that you are actually focusing your learning on certain difficult examples, possibly, as the learning proceeds. But that's an excellent observation. In fact, even though the original classifiers were just horizontal and vertical lines, the consensus classifier actually is going to be a combination of them, so it can actually be a jagged surface. Yes.
So could you remind me how we're defining the weak hypotheses? Like, are they always aligned?
In the tiny example that I had, so actually this algorithm, if you think about it, needs two sets of inputs. One is your training set, the other one is a learning algorithm. It takes a weak learning algorithm, repeatedly keeps applying that, and in the toy example that we had, it was just lines, but it could be any weak learning, any learning algorithm potentially. And in fact, that's why ensemble methods are called meta learning algorithms. They take a learning algorithm, repeatedly call the learning algorithm to produce multiple classifiers and combine them. So this is a function that has two parameters, a data set and a learning algorithm, and produces a classifier that's a combination of many classifiers. So everything is easy here. We know how to find a weak hypothesis because it can be any learning algorithm. What we don't know is how to construct a distribution and how to construct the final output. If I can specify these two, then I'm done. Right? So if you know how to construct a new distribution and how to construct the final output, you can implement this procedure. Because the middle step is any learning algorithm. So it turns out AdaBoost gives us instructions on how to do each of these things, and if you follow those instructions, you get all the guarantees that AdaBoost comes with. So let's talk about AdaBoost. You have m examples. The distribution is just a set of weights over each example, and so you have m weights, d1 through dm, each of them at a different time, one for every time step. So what you do is initially, as a few of you pointed out, use the uniform distribution. All examples are equally important. So d of I is 1 over m. We play this game for many rounds, and after d rounds, say we have a distribution dt. We call the weak learning algorithm. It creates a new classifier for us. Let's call it ht. And that classifier has an error epsilon t. And remember, error is the weighted error, weighted according to dt. It's not the same error that we've been looking at all the time. So it has a weighted error of epsilon t. Now our goal is to somehow use what we know at this point, dt, ht and epsilon t, to construct a t plus 1. Question?
Can we think of it like running epochs on the examples like we did for the perceptron?
No, we are actually, yeah, that's one way of doing that, but so let me repeat the question for the ones who did. Can we think of this process as running epochs over the examples just like we did for perceptron? It turns out actually it's more than that, because we are not running epochs because the weak learner itself might run multiple epochs internally. The weak learner is a black box. It could be a perceptron that runs multiple epochs over the data. This is multiple epochs over the weak learner. So now our goal, just to remind you, is we need to construct dt plus 1 given dt, h and epsilon t. And what we need to do is somehow use, define dt plus 1 so that whichever examples were incorrectly predicted get more important, and whichever examples are correctly predicted become less important. And in other words, we want to increase the importance of the misclassified instances and decrease the importance of the correctly classified ones. And what AdaBoost recommends, or actually demands even, is you set dt plus 1 to ignore the z here for now. If an example I, if a data point I was correctly predicted, something say like this one, what you do is you multiply it by e power minus alpha. I'll tell you what alpha is in a minute, but you multiply it by e power minus alpha, and if you choose alpha correctly, this number goes down. It's basically multiplying by a number less than 1. If you made a mistake, you multiply it by e power plus alpha. So you promote it. So, and the z here is just a way to make sure that all these dt's add up to 1. It's just a normalizing constant. So I can combine these two things by saying dt plus 1 is dt of I times e power minus alpha times y times h. Y times h, remember, is minus 1 if you make a mistake and plus 1 if you get it correct. And we've been seeing this since we saw perceptron and the linear classifiers. Because y and h are binary, this works. A way of checking for mistakes is multiply y and h, and if it's negative, you made a mistake. So you construct dt plus 1 by either promoting or demoting each exam questions about this.
Alphas are linear, right?
Alpha's just a number. H is the classifier, y is the label, alpha is just a number which I'll be defining in a minute.
Okay.
It's a number that's actually a function of the error that classifier made.
Do we need to apply the weak learner to all examples? Because in the beginning you said that you choose a subset of the...
No, you don't choose a subset. You choose the entire training set. In the beginning, all examples are equally weighted. You just start moving you create a distribution over these examples and move the weights to examples that are consistently wrong, that wherever you make mistakes, and you use the entire training set to produce a weak learner. The initial example that I said, where you choose a subset, that was mostly as a motivating point. This is the boosting example. There are actually ensemble methods where we only choose a subset, but not for our boost. So if you have this update rule for the examples, so just a minor points of clarification, we still need to define alpha and z. Z is just a normalization factor. Z is constructed so that all the di's, when you add up, it sums up to 1. So it's literally just the sum over all di's. Sum over all the unnormalized di's. There's nothing fancy there. You can just, we know how to take a bunch of numbers and make them add up to 1. You divide by the appropriate constant. Alpha, and this is the nice bit here, alpha is defined in terms of the error. So, for example, if your error is, say, 0.5, then alpha is 0. Or actually not 0, it's log of 1, which is actually 0, yeah. So if the classifier makes an error that is exactly chance, then alpha is 0. If the classifier makes an error that is, say, close to 0, in the limit, let's say epsilon is very, very, very small, then this quantity here, the numerator becomes close to 1, this becomes close to 0, the log of this is a large number. What this means is, if the weak classifier is very good, then its corresponding alpha should be very high. Okay? And so if your classifier was very good and the corresponding alpha was very high, then look at the promotions and demotions. If alpha is very high, those examples where this classifier was correct with get really demoted strongly. So they become very unimportant, and intuitively the way to think about it is, there is this one weak classifier which is really good on these examples. Let me take them out of the learning pool. There are some examples which even such a good classifier makes a mistake on. Let's focus learning only on those for the next round. Now alpha actually plays a double role. Alpha shows up also to, alpha is used to weight examples this way. I mean reweight examples. But remember, in constructing the final classifier, we had a vote for every weak classifier, right? It turns out the alpha is also what the weak classifier gets in the final, the say of that weak classifier in the final output. So it's the vote that the weak classifier gets. Again, the way to think about it is, if a weak classifier, HT, is very bad, let's say its error is 50%. It's exactly chance. This is literally just tossing a coin. Then alpha is log 1, which is 0. So if this classifier is just tossing a coin, it should not get any votes in the final output. On the other hand, if there is another weak classifier whose epsilon t is really small, then alpha is really large. So here's a weak classifier that's really good. Then this classifier should get a very high vote in the final output. Questions? Yes.
So one hypothesis is alpha depend on the order you get those hypotheses?
Yes, in fact, this is that's a good observation. This algorithm proceeds in a certain order, the meta algorithm. So, yes, you're right, but I suspect that's not your real question.
That seems like a bad thing.
Why?
Isn't it?
Why?
Because then you'd have to know which hypothesis you want to give more or less weight to.
But you let the hypothesis, the weight of the hypothesis be decided by error it has. So you want to have good hypotheses be more important in the final output and bad hypotheses disappear. Right? But you're right, it is actually sequential, and in fact because alpha does this double duty of both reweighting examples and deciding how important a classifier is. If a classifier does very well on some examples, it's going to directly influence through alpha the next classifier that gets chosen because of this reweighting. Other questions? Yes.
So alpha is not specific to an example, it's the global.
Alpha is it's computed based on epsilon, which is simply the error. It's based on the entire training set. It's a property of the classifier and the DT and the training set.
So wouldn't you get an idea to have alpha specific to a given set of examples so we know that that algorithm is doing well on this set of examples?
How do you know which examples are going to come in? We don't have any way of... I see your point. So let me try to paraphrase what you just said. If I know that my classifier is very good in this region of the example instance space, let me just remember it, and when a new example comes in from that region, I'll use the one that's good here.
That has the one greater vote.
That has a greater vote. But unfortunately, we don't directly have that information. That's another classifier which decides which region, how to partition examples. Right? So we don't have that information at test time necessarily. So let me just go back a bit to decide. Yes.
Sorry, has anyone ever done a k closest neighbors with to determine which algorithm to run on examples?
Yeah, people do that. There are a few such things where you partition, and these are typically, they show up in more application papers than necessarily in the learning papers, where you don't necessarily care about algorithmic beauty. You want that thing to work. So those things, such solutions do show up. So yes, just to go back a bit, boosting is the setting where you're given a set of training examples and you proceed in rounds. You have as input to this meta algorithm, there is another learning algorithm. So at each round, you construct a distribution over the examples and then run the weak learning algorithm, find a hypothesis, and just remember that hypothesis and compute an alpha. And you remember these two things, the alpha and the hypothesis, and you construct the final classifier. And I just told you in AdaBoost how the distribution is constructed. The next thing that's left is to decide how the final output, which is H is actually a function, how the final output classifier is constructed. There's no math. It's not terribly hard because I've already given away the answer. After t rounds, we have t classifiers, h1, h2, all the way to h3, ht. And for each classifier, we've computed an alpha. Alpha 1 through alpha t. And now at the end, we have to now construct a final classifier. Just to remind you, remember that each h is itself a function. H is a function that takes an example and produces true or false. Our goal is to combine all these functions. And the way we do that is to simply take the linear combination of the output of these functions and basically weight each output by alpha t and take the sign of that. So in some sense, the final output is a linear classifier over other classifiers. Questions? Yes.
Do we need the algorithms in each round the same?
Which algorithm?
The weak learner.
No, it doesn't. In fact, we don't. There's nothing here that assumes that, right? You can call more different learning algorithms at each step. All we care about is whatever algorithm you call should be a weak learner. Because if, for example, the epsilon is less than half, so alpha becomes log of 1 minus epsilon divided by epsilon. So it becomes negative. Right? Sorry, yeah. Did I say that right? If epsilon is more than a half. If the classifier if the classifier has a training error that's more than half, then that classifier gets ignored. In fact, this procedure learns the following. It learns to say that this classifier is actually made a mistake of more than half during training. So let me run this classifier, get its decision, and reverse it every time I have to make a prediction. Because alpha becomes negative. So we don't care about what the weak learner is, we only care about the fact that it should be a weak classifier according to the definition we have. So let me summarize this whole process. What we have, this algorithm is called AdaBoost, and the input to this is a training set, and what is not mentioned here is also a weak learning algorithm. You initialize, for every training example, you initialize a set of weights, di, and set it to the uniform distribution, which is just 1 over n. And then you proceed in rounds from 1 through t. At each step, you find a classifier whose weighted classification error, whose epsilon t, is better than chance. This is the error of that classifier. And then you compute an alpha t for that classifier according to this expression here, and then update the weights. Just 3 steps. You learn a classifier, compute an alpha, and then update the weights to promote the examples where you made a mistake and demote the examples where you were okay. Do this t times, and at the end you return a final hypothesis, which is this combination of the alphas and h's. And the only thing missing here is t, and t is just a parameter. It's a hyperparameter, just like the number of epochs in perceptron. How many weak classifiers are good enough? Questions about AdaBoost? Yes.
I have a question about the weak hypothesis. If, for example, a hypothesis is making the error of it is 99%, for example, then is it a good thing or?
No, it's a bad thing. If the error is 99,
the reverse and the outputs, then the error is 1%.
Right. So actually, I see your point. In fact, that's what happens here. If in general, if I tell you, that's a good point actually. If I give you a classifier whose error is 100%, let's say, I would argue that it's an excellent classifier. It's just perfectly wrong every time. So I run the classifier and then just reverse the decision. Right? And that's what this process does. If the error is 99%, epsilon is 0.99. So log of 0.01 divided by 0.99, it's a negative number. So that classifier gets a negative weight. So from the algorithmic point of view, it's okay. But in order to prove the theorem, we assume that the error is less than half. So let's just quickly go look at the toy example. We had 3 weak classifiers. None of them were good enough. And each of them came with its own alpha. And the final hypothesis is this combination of these classifiers. And as someone pointed out, the final decision boundary does not have to be either the horizontal or the vertical line, and in fact it will be something like this. The final decision boundary will not be any of the weak functions that we had. It will be some combination. So we have now, by doing this process, what we have done is we have effectively gone to a richer class of functions without explicitly considering it. So what I have just given you is an algorithm. What I have given you is actually just some pseudocode. Anyone can come up with pseudocode. Without a theorem that proves it's good, it's as good as not having anything. So, yes?
Does this other class of functions ever get as rich as k-nearest neighbors, or as k-nearest neighbors pretty much the epitome of how complicated it can be?
This can actually, we'll see, I'll show you some pictures. This can get arbitrarily good on any training set. In fact, typically when we run AdaBoost, we will run it till we get 0 training error. We can represent any set of tables. But with infinite number of examples, k-nearest neighbors is, or 1 nearest neighbors is guaranteed to give you the right function. I have to think about whether this has a similar guarantee. I suspect it won't be hard to prove anything with infinite examples, because it's such an easy case. You have all the data you need. But what we can prove about AdaBoost is actually a statement about the training error. And I'm only giving you a flavor of this theorem. There are some notes on the website which actually states the formal theorem and the proof, and I strongly recommend that you go over the proof. I'm actually not doing the proof because I don't have time, but I would like to do it. And it's quite easy actually, and it's just a few steps. But the theorem itself is the following. Let's say you run this AdaBoost algorithm for t steps. And at every step, you have this weak classification guarantee, which is you have the error of each classifier is some epsilon which is less than half minus gamma t. And suppose there is this gamma which is really small, which is the smallest one of all these gamma t's. Let gamma be some number which is smaller than all the gamma t's that showed up. Then the theorem says the training error of the final classifier, meaning error of the final classifier on the training set, will be less than e power 2 gamma minus 2 gamma square t. What it means, let's just step through this. The condition on the epsilon t simply says we have a weak learner. That's it. And this bound on the training error says as t increases, the error on the training set drops off exponentially. So if you keep running AdaBoost for more iterations, your training error goes down and goes down really fast. So there's a proof, as I said, there's a proof for this on the website, and I encourage you to look at it, but something to think about. Is it okay? I mean, here's a statement about the training error. So what? I know an algorithm that gives me 0 training error, the decision tree does that. So is it sufficient to just give a bound on the training error?
Does the hypothesis final also have a good, general error?
We don't know, right? On the other hand, what we do know is the theorem from the agnostic learner. The generalization error is bounded on top by training error plus another term which is some combination of the complexity. So reducing the training error is always a good thing, provided we have this capacity control.
But doesn't this allow us, what would be the complexity of the function class when we use this?
It depends on the complexity of the weak classifier. So it can be arbitrarily complex.
Okay.
Yes, so that's the problem. In fact, yes.
Just as with K and neighbors and decision lists, could we be overfitting our data?
Very good question. We almost certainly will be. So let's look at some graphs on real data. So first of all, if I just run AdaBoost on some, I don't even know what this data is. If you run AdaBoost on some training set, the training error drops off exponentially. The blue curve is the training error. And very, very often you get to zero training error very quickly. This is the training error of H final, the combined classifier. This doesn't mean that this little h at every time step keeps getting better. In fact, very often these little classifiers, the weak classifiers, tend to get worse as you see more and more examples. As they get worse, it's okay because they do not contribute to the final classifier too much. So, observation number one, training error theoretically drops off exponentially and in practice ends up going to zero very often. As we all know, the real deal is not the training error but the test error. And we know two things that the theory tells us. The theorem from AdaBoost tells us that the training error drops off exponentially. So that's the curve at the bottom. As the number of rounds increases, you get lower and lower training error. What we know about Occam's razor and PAC tells us that as your final classifier becomes more and more complex, which is what is happening, right? Every time we add a new weak classifier, we are making the final classifier slightly more complex. And as the classifier becomes more and more complex, after you hit a certain sweet spot, the test error starts getting worse. So this means you are actually overfitting. So in an ideal world, what you would like to do is stop at this sweet spot. So stop somewhere here, let's say. So run into those many iterations and stop. Unfortunately, we have no way of doing it. So this is what the theory tells us. Now here's the weirdest thing that happens very often in AdaBoost. In practice, the red line here is the test error on some held out set and blue is training error, and the test error really doesn't increase, doesn't seem to overfit, and in fact even after, in some cases it turns out that even after the training error hits zero, if you just run AdaBoost multiple times, sometimes the test error decreases. So your training error is zero, epsilon is zero, so you will not change the distribution, you just find a new classifier and you get a new classifier and the test error decreases. And this was a puzzle that kept many people awake at night for a few years. And if you're interested, there's actually a way to reason about this within the PAC framework, about proving why the test error might decrease. There's a paper about that and you can take a look at it. So let me quickly summarize AdaBoost. It's easy. It's really easy to implement. All you need is this weak learning algorithm and the rest of it is just literally 10 lines of MATLAB. It's fast. Its complexity is entirely a function of whatever weak learner you have, and your weak learner doesn't have to be really difficult because it's a weak learner. And it doesn't really look into the guts of the weak learning algorithm. You can use it with any learning algorithm you want, as long as it can account for these weights. Unfortunately, the performance of this classifier depends very strongly on the performance of the weak learner, and it suffers from overfitting and underfitting. The key lesson, which I may have mentioned before, and there's no harm in mentioning again, is there's no magic here. You can only get as much signal out of your data as there is signal in your data. That said, there were actually a series of papers in the mid-2000s which said that if you have no constraints and you don't care about what learning algorithm you want to use, and you have a small set of features, say 300 or something like that, then probably one of the best things to do as a black box classifier is to use boosted decision trees. Run AdaBoost on, not boosted decision stumps actually, run AdaBoost on decision stumps. So you have a decision stump, just to remind you, is a decision tree like ID3, what you learned right at the beginning of the semester, but you limit the depth to say 2 or 3. That's your weak learner. And if you have, the boosted decision stumps are an excellent general purpose learning algorithm, and Rich Caruana and a student, they showed that they showed this empirically by running, I don't know, about 20 different learning algorithms on 300 different data sets, and invariably boosted decision stumps came out at the top. These were all somewhat small scale problems, but still. Questions about AdaBoost? Yes?
How do we ensure that our weak learners are sensitive to the importance? If we use KNN as our weak learners, how do, if the weight is increased, and then how do we?
Right, so you have to play with the distance. You have to be, for KNN, for example, you have to play with the distance. For perceptron, you have to play with the notion of error. In fact, for most of them, you have to play with the notion of error. For perceptron, for Winnow, and such things. You can play with the learning rate as well. You can, for example, in perceptron, if the learning rate is R, you don't have the learning rate R, but R times the importance. So if I make a mistake on an example that is not important, you don't make a strong update. If I make a mistake on an example that's important, you make a big update. So that's for perceptron. For KNN, you play with the distance function. If you are close to an example that is important, you try to predict a label that has that point.
So we need to make some modifications?
Yes, absolutely. You can't just use the algorithms that you already learned. You need to make modifications, but very often, I must add that these modifications are fairly simple. As I said before, you just need to think about what this algorithm is doing and how effectively every algorithm we have seen so far is treating all examples as equally important, implicitly. So you need to think about where this importance factors in and make a change. And typically these are minor changes to the existing code. Other questions? Yes.
Assume we have some data set 4 dimension, and we have like some weak learner on dimension 1 and 2, and another weak learner on dimension 3 and 4. Is that possible to combine these two?
Yes, absolutely.
So we can use different dimensions.
Yeah, you can, yes. Other questions about AdaBoost? Yes.
So for that empirical evidence, is there any intuition why the size of features is important?
I have to think about this. So one way of thinking about this is if the number of features is very large, intuitively it turns out if your dimensionality is very large, linear classifiers tend to be very, 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 very hard to beat, because most concepts are almost linearly separable in very high dimensions. So the lesson from that paper was, if your dimensionality was large, use a linear classifier. If your dimensionality is small, use boosted decision stumps. If this was 2006, it's been a decade almost. Since then we've learned a lot more, and if you have large dimensions, we know a little bit more of what else we can do, but for lower dimensional spaces, this certainly holds. Yes? Can you speak up?
Can AdaBoost be used for feature selection, or is there a...
In fact, here's a thought. AdaBoost is actually doing feature selection. If you think of each weak classifier as a feature, this weak learning algorithm is a heuristic that creates features that are important. Suppose AdaBoost is actually iteratively picking a good feature. If instead of thinking of the weak classifier as a classifier, if you think of it as a feature, AdaBoost keeps picking good features as you go along.
So it will be the feature instead of
It,
classifier. So the edge will become a feature.
edge becomes a feature. But then, that said, there is no magic in the universe, unfortunately. If you think of it that way, actually what AdaBoost is doing is minimizing something called the exponential loss, and it's very close to things like logistic regression and SVM. It just so happens. But we'll see that once we come to loss minimization. Okay, in the 10 or so minutes that are left, I'm going to quickly talk about ensembles. In particular, I'm going to very briefly introduce, in maybe a minute per item, 3 ensemble algorithms. The general recipe for ensembles is that it's a meta algorithm. It's an algorithm that takes a learning algorithm as a parameter and produces a hypothesis that's the combination of multiple classifiers. And empirically, these tend to be very, very robust. And there are good reasons from statistics for why ensembles are good. They're not only good in theory, but in practice they've been really, really useful. Just as an example, the name of the team that won the Netflix challenge was called Ensembles. The classifier they produced was an ensemble of ensembles. So they just kept piling together multiple learners.
Just out of curiosity, was the Netflix challenge the one that created House of Cards, or was that something else? House of Cards, you know, you've heard that show, right?
Yes.
Apparently that was found by machine learning.
Okay, I have no idea.
Okay.
This kind of, we haven't talked about it, but this kind of reminds me of neural networks where you
It's in a similar flavor where you're building a meta classifier in a neural network, in a multi-layer neural network. If you think of the inner nodes as weak learners themselves or weak classifiers, you're building a consensus decision. It's a similar sort of a flavor, but this comes from a different background. Okay, so quickly, boosting is, we've already seen boosting, so I'm not going to spend too much time. You just have weights for each example and you run this multiple times, sometimes hundreds or thousands of times. And the output is just this committee. And AdaBoost dictates how you choose the examples, how you do the weighting, and how you construct the final output. This algorithm has been analyzed to death. There are many ways of looking at it. There was a paper from Rob Shapiro. This was the one I told you about a little while back, which I encouraged you to read it if you wanted to know why boosting did not overfit. It said that boosting was maximizing the margin. Remember the margin we were talking about when we saw perceptron? Turned out this was actually an algorithm that maximized the margin. Statisticians, Hasty, Tripshirani, and Friedman, they proved that boosting is actually a logistic regression model. Bryman called boosting an equalizer. I'm not sure why. It's a linear classifier, clearly, because it's linearly combining multiple classifiers. Another ensemble method called bagging. Bagging is short for bootstrap aggregating, with careful selection of characters from those words. And it's a pretty easy algorithm to implement. Say you're given a training set. What you do is sample examples from this training set with replacement. With replacement means the same example can show up multiple times in the sample. You sample a subset, train a classifier. Just remember it. Sample another set of examples, train a classifier, remember it. Do this many times. And the final classifier is just voted. Every classifier gets a vote. This is called bagging. And bagging actually has some history going back to the 70s from the statistics literature. It goes back to this idea called bootstrap method. Those of you who may have taken more than one statistics class may have seen the bootstrap. And it's a method of, it's actually a very easy algorithm to implement. You just need to sample examples. There is no confidence weighted learning or anything. You just use the learning algorithm you already have. You take a subset with replacement, train, and do this multiple times. And you can average it for regression, or you can just do voting for classification. There are a few ways of thinking about it, but the most common way of thinking about it is you effectively train multiple classifiers, and the hope is by taking bootstrap samples, and bootstrap samples are samples with replacement. You train multiple classifiers, and the hope is these different classifiers will, on the average, be better than any one of them, because the errors will get cancelled out when you take the vote. And it turns out that on real data, they tend to work very well, and they are actually, again, very easy to implement. It tends to work well when you take your training set and make a tiny perturbation to it, and if that changes the classifier, this means that the classifier is actually very sensitive to the training data, to noise in the training data. So you try to get rid of that noise by sampling multiple data sets from your training set and averaging them. Just as an example, there's something called a bag decision tree. Here's the algorithm. You draw many bootstrap samples. Bootstrap sample is just statistics speak for sampling with replacement. You draw many bootstrap samples of the data, and for each set you train a tree. You get T trees. And then you just average the prediction of those trees in case of regression, or you take a vote for each tree in case of classification. That's it. You can go a little bit more. Random forests are basically bag decision trees with a tweak. Same process. You take a bootstrap sample of the examples, and you also take a subset of the features. You use only those features on this bootstrap sample to train a tree. And you do this multiple times, and you average it out. Does it make sense? Questions? Either everyone got it or no one did. Yes.
Does this work well when you have like small sample sizes? Or
Yes. If your data set is very small, or if your data set is not all that good, meaning there's noise.
Or like maybe does it work better as well if you have very few levels of one feature maybe?
There you have to be careful, because what might happen is that feature might either get lost or things like that. So you have to be a little careful with your sampling. You might have to stratify things a bit. Yes?
So if you want to do stumps instead of trees, would each of those just be a stump? Or
Yes.
would each of those be like a collection of stumps?
Each of them is a stump. Yes. Okay, so let me wind up. We saw boosting, and boosting historically is an answer to a question that came into existence because of pack theory. Does weak learnability imply strong learnability? AdaBoost is a constructive proof that says yes, weak learnability implies strong learnability in the form of an algorithm. And it works because it drives the training error close to zero. It exponentially decreases the training error. AdaBoost is just one instance of a large family of algorithms called ensembles. And if one lesson from this class for this lecture for after the semester is, if you have a very small data set or if you have very few features, consider ensembles. They tend to do well, especially, and they are actually favored quite a bit in industrial strength classifiers. If you go to in places like Netflix, for example. So there's good reason to add this to your toolbox. Reminder, no office hours today, and a lot of things are due all the time.